Good evening, everyone. So, sorry for the slight delay. There was some technical issue at my end. I was just sorting it out. Okay, so let's start the live session. Um, Mahesh, can you please mute yourself? Thank you. Okay, everyone. So, I'm Niketa, and I'm a PhD student at IIT Madras, and I'm your TA for the industrial wastewater treatment. And Mahesh, can you please mute yourself? Yeah, thank you. So this is week 4 of the live class, and before we start, I want to ask if you have any questions or doubts from this week's lectures or from the previous week's lectures. So if there are no doubts, then we can proceed with this week's lectures. So this is week 4. So in this week's lectures, we'll be looking at some portion of advanced oxidation processes and majorly on membrane processes. So yeah, last week's lectures were more about AOP's advanced oxidation processes. So we'll be continuing with that. So coming to UV disinfection. So disinfection is majorly done to remove any microorganisms, especially bacteria, present in drinking water. So since they are harmful for our health, that's why it's important that we remove them by destroying them completely. So for this, we use a variety of methods. So UV is one of the more sophisticated techniques out there. So what happens here is UV radiation, it will penetrate the cell wall and thereby it will destroy the DNA after penetration. And by destroying the DNA, it ensures that it cannot multiply further. So once the cell wall is broken, so the cell eventually dies, and once the DNA is also damaged, then it ensures that it cannot multiply also. So for this treatment, the water needs to be in contact with the UV light. So it can be classified into two categories based on the intensity that is required. So the first one is low pressure. So this generates low intensity monochromatic light. And the second one is medium pressure. So here the radiation is high. So it is a high intensity radiation. And this can be scaled up, so it has applications in the large scale also. And it has 15 to 20 times more germicidal capacity. That means it can kill 15 to 20 times more germs compared to uh, the low pressure lamp. But the only drawback is it needs a large amount of energy. And when it operates at a high temperature also. So the radiation, I mean disinfection, depends on two things. One is the intensity of the radiation. So, like I said, medium pressure has a higher intensity, so that's why it has a 15 to 20 times more germ killing capacity. And it also depends on the distance. So because we are talking about UV radiation, so as we increase the distance between water and the UV radiation, the UV light intensity will reduce and it won't be able to travel for a large distance. So that is why we have to keep the UV lamp in close contact with the water that needs to be disinfected. So ideally, it will be like a tube where inside there will be an UV lamp. So this will generate UV radiation, and so water will be passing through, and it will be coming out. So here in between there is the UV lamp. So the UV lamp will be turned on so that water will pass through this tube, and as it passes through, it will uh, it will take the radiation and then it will come out. So we can optimize the temperature, the time for which it is going to be in contact with the UV radiation also. So thereby we can maximize the degradation the disinfection. So the radiation of UV that is most useful for disinfection is UVC. So there are other types of radiations also like UVA, UVB, and so on. But UVC is the most effective for microbial degradation, and that is because it is that's the only kind of radiation which is absorbed by the DNA and the RNA of the microbes. And other than wastewater or water treatment, it can also be used for air purification. So the advantages of UV radiation is that there are no chemicals involved. Like in case of chlorine, we have to add chlorine salt like hypochlorous. As we have to add chlorine externally, so then it will produce Cl, HOCl, and OCl minus ions. So these will form some organic products along with the degradation of microbes. So in that case, it will form organic chlorinated products, which are also byproducts of the disinfection. So this chlorinated byproducts are slightly it is toxic and also not good for health. So that is why that is one disadvantage with the chlorination technique. But otherwise, it's very good. It has an advantage over the UV process and the UV process because when you add chlorine to water, you don't have to repeat the dosage very often. So you just have to add the chlorine and then you can transport the water for maybe a few hours to maybe one day. So that you can give it some time. But in case of UV radiation, the disinfection happens as the water comes in contact with the UV radiation. So once it has come out, then if there are any residual microbes still in the water, then they can multiply. So there is nothing that's stopping them from multiplication. So unlike chlorination, UV radiation has this one disadvantage. But in case of chlorination, since we are adding chlorine to it, it is going to stay as residual chlorine, and then that is going to prevent any further multiplication in case there are any residual microbes. And it also requires less contact time. So in for chlorination, we have to maintain a separate chlorination tank where we have to give it a retention time for it to mix well with the inside the water and so on. But for UV, there is no such requirement because the energy intensity of the UV radiation itself is very high. So it can do its work in a very short span of time. It just has to radiate and penetrate the cell wall. So that can be done in a fraction of a second. So that's why it doesn't require any contact time. So the water can just pass through and come out. And while it does so, it will be disinfected. And also the microbes in UV radiation, in case of UV disinfection, they can once the UV radiation is removed, the residual microbes, if any, they can multiply and they can grow also. So that disadvantage is there. Okay, so now we have seen UV disinfection. Let's come back to AOPs. So we have seen what advanced oxidation processes are. So, advanced oxidation processes use free radicals or just oxidizing radicals. Like hydroxyl or sulfate and O2 superoxide. So all these radicals are there. So there are some chemicals called scavengers. So what these scavengers do is they react with these radicals and they form some products. So because the radicals get used up in this reaction, there won't be any radicals for the oxidation of pollutants. So that is one thing we need to be careful about. We have to make sure that there are no scavengers in our advanced oxidation process reaction. So one example of a scavenger is carbonate. So CO2 3 CO3 2 minus. This reacts with hydroxyl and it will produce carbonate radicals. So these carbonate radicals are not very active. They are slightly less reactive compared to hydroxyl radicals, and therefore the efficiency of the advanced oxidation process will come down. And in UV based advanced oxidation processes, we have to ensure that there are no suspended solids. So the reason why we should not have any suspended solids is because if these suspended solids are present, then they will scatter the UV light and they won't allow the UV light to penetrate through the water, and therefore the pollutant oxidation cannot happen effectively because only if UV radiation is there, hydroxyl radicals will be generated and hydroxyl radicals will break down the pollutants. But if suspended solids are there, they'll scatter the light and they won't allow the penetration to be effective. So, this phenomenon where the UV radiation gets wasted is called light wasting. Basically, the light is entirely getting wasted because it gets scattered instead of absorbed because of the presence of suspended solids. Okay, now coming to the drawbacks of UV based processes. The first one is, of course, the cost. So, since it is UV radiation, generating UV radiation requires a lot of electricity and current. So, the power requirement is high. So, when there is a high power requirement, obviously the cost is also going to be higher. So, we need a high operational cost. So, there are two types of costs when it comes to any process. One is the operational cost, and the second one is the capital cost. So, capital cost is the cost for establishing something. So, for example, if we have a wastewater treatment plant, so we are trying to build a sewage treatment plant, and for building that sewage treatment plant, which will run for maybe 25 years, so accordingly, we have to design and we have to build all the units. So, for building that, we need to spend some money. So, that is the capital cost, which is the establishment cost or the cost for uh, building or buying something. So that is the capital cost. The second one is the operational cost. So operational cost means once you have the STP established, once you have built the STP, now you need to run it. So for running it, you will need some money. So in the form of for buying electricity, for buying chemicals which are required every day to be added to the STP. We need to have sufficient manpower, labor to ensure that the sludge is removed on time. So, all of this is operational cost. So, operational cost means daily cost or cost involved in operating the facility. So these are the two types of costs, not just for this process, for anything like any kind of process. There are two different types of costs. So when it comes to UV based processes, both operational as well as the capital cost is going to be high. Operational cost, like I said, because it is UV radiation, the electricity requirement is high, so that is why there is a an expense. But even the capital cost is high because this is a photolytic treatment. So we need to design in such a way that the water is coming in contact with the UV radiation without actually damaging it. So there are some infrastructure wise we need to plan and we have to have the sufficient I mean, we need to have the infrastructure we can actually facilitate this process. So that is why we need to go for I mean, the capital cost is higher. And because UV radiation is directly linked to cancer, so exposure to UV radiation is known to cause cancer. So the reason is it doesn't just damage the cells of microbes; it also damages human cells also. So especially if it is exposed on the skin, it can lead to skin cancer, and because of that, we there is a safety concern. So it is not very safe, especially for those who are operating it, laborers, etc., who are involved in this process, who have to work in a UV treatment plant. So they need to be extra careful. So they have to wear extra protection. They need to be wearing sunscreen. So all this to prevent the UV radiation from damaging their skin cells. So while quantifying advanced oxidation processes, there is a term called energy efficiency. Per log removal. So what this means is the amount of energy required for removing 1 log. So 1 log usually means about 10%. So if we have something, initial concentration is 100%. So to ensure that the removal is 90%, so from 100 it is coming to 10%, so minus 90%. So this 90% removal equals 1 log. So the amount of energy which is required for removing 90% of the pollutant equals the energy efficiency per log removal. So energy efficiency per log removal is how much energy is required for 1 log or 90% removal of the pollutant. Okay, so now we come to membrane processes. So membranes, they are usually used for filtering or removing the solids present in the water. And these days we have nanofiltration, RO, all of this. So these can remove not just solids, they can also remove ions. And then there are some terminology which is related to membrane processes. First one is permeate. So permeate is the solution or the liquid which is passing through the membrane. And this is the retentate. So retentate is the liquid which is retained. So retentate means like when you have the membrane like this, so it has got some pores and water is flowing in this direction. So only water is allowed to pass through. So the water that is passing through the membrane is permeate, and whatever solids are not passing through, they will be retained here along with a small amount of water. So that is called the rejectate. So the reject will have a higher concentration of the ions compared to your initial feed water. That is because whatever ions are there, they are retained here, and this retained ions will be mixing with some of the water also which is present on this side, and eventually that concentration will be higher in the retentate compared to the permeate concentration. So here the concentration of the permeate will be lesser than the feed concentration, but the concentration of the retentate will be higher than the feed concentration. And the next term is flux. So flux is the rate of liquid flow per unit area of membrane. So it is the amount of liquid which is flowing through per unit area of membrane. It is expressed in meter cube per meter square hour. So that is the unit of flux. And the next one is fouling. So fouling, like you must have seen in the lectures also. So fouling means the membrane pores get blocked because of the accumulation of particles, microbes, or organics. So this will reduce the efficiency of the removal. And how can fouling be removed? There are two methods. So the first one is cleaning in place. So this is done by backwashing. So backwashing, like we've seen in the previous week's lectures. So basically, if this is the direction of flow, and your membrane here is blocked with the solids or microbes or whatever, and water is not able to pass through, then what happens is we take the blocked membrane and we reverse the direction of flow. So we provide water in the reverse direction so that whatever solids are there, they get dislodged and removed. And after that, the membrane becomes back to normal. It will, it won't have any blockages. Okay. This is cleaning in place. Cleaning in place doesn't require the membrane to be moved. So if the membrane is already fixed in a place, then we just have to reverse the direction of flow, and we can do backwashing. And we can also take the membrane out for out of place cleaning. So this means the membrane is removed and it is washed somewhere, and then it is placed back into its place. And for any kind of membrane process, we need to provide pre-treatment. So pre-treatment will ensure that the organic load or the solids load is not very high on the membrane. Reason why we do this is because if we don't do pre-treatment, then there are very high chances of fouling happening, and the fouling can happen immediately also if we don't do pre-treatment. And after the treatment also, we have to do post-treatment. Now, why we need post-treatment is the removal will not be effective, as required by the standards. For example, maybe if the requirement is 1 ppm, and if your membrane is only able to remove up to 10 ppm, then we need to provide post-treatment also, so that whatever remaining pollutant is there, that is also completely removed, and it is it is following the standards. So when it comes to membrane processes, the selectivity of the membrane is very important. So selectivity means the ability of the membrane to distinguish or to separate the different pollutants based on the size or charge. So selectivity is what determines what will pass through the membrane and what won't pass through the membrane. So this is based on the size and charge. So size, I've already we've seen how if the pollutant size is larger than the pore size, then it won't be able to pass through the membrane. But if the size of the pollutant is small, then it can easily pass through. And also the charge, because if your pollutant is negatively charged and the membrane is positively charged, then there will be some kind of attraction between the membrane and the pollutant. But if both are having the same charge, then there will be repulsion. And because of repulsion, the pollutant will not be sticking to the membrane surface, rather, it will be flowing through the permeate or the pore. So when it passes through the pore, also the charge difference can lead to attraction, and the pollutant may get retained at the pore itself. But if not, then it will be flowing out. Now we come to the classification of membranes. Okay, membranes can be classified into microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So microfiltration, the membrane size is between 0.1 to 10 micrometers. So microfiltration is used for removing mainly suspended solids, bacteria, and large colloids. Whereas ultrafiltration is the size is between 0.01 to 0.1 micrometer. As you can see, it is smaller than microfiltration. So this can remove viruses also, and it can even remove some kind of proteins and some macromolecules. And then nanofiltration, the pore size is between 10 power minus 3 to 10 power minus 2 micrometer. So this is in the nano range. So 10 power minus 3 micrometer equals 1 nanometer. So like I had mentioned before, so nanofiltration, as we go to smaller and smaller pores, they also can remove ions and dissolved organics. And even color. And finally, RO. So RO can, RO has the size of 0.1 nanometer, and this is done for removing salts. Mainly, it has applications in desalination. So you must have heard of desalination plants. So where we make the seawater flow through the membrane, and whatever salts are there, they get retained on the membrane itself, giving us clean water. So RO is the membrane which is used for that purpose. So it has a size of 0.1 nanometer, and its main application is in the desalination and also for removing uh, dissolved ions. So whatever RO plants that we have at home, basically they don't have as many ions, but still there are some ions, but it's not like completely deionized. So if we want to go for deionized, then we need to pass it through RO again. And RO, because it is having a very small pore size, we need to apply high pressure for the water to pass through the membrane. So the pressure is usually 10 to 150 bars, which is very high pressure. Okay, this is about membranes. So here we have to apply some external pressure for the water to pass through the membranes, and the pressure will increase as we go from a large pore size to a smaller pore size. Now we'll see about electrodialysis. So electrodialysis is similar. So there is a membrane through which we pass the water to remove pollutants, but the difference is that there is also an electric field, and the membrane used is ion selective. Means depending on the type of ions that we want to remove, we can select the membrane. And Here an electric field is also applied. Now we'll see about the mechanism which is involved in membrane separation. The first one is mechanical filtration and sieving. So mechanical filtration means like if you have a pore, so imagine we have this membrane and there is a pore here. So the particle will pass through the pore if the size is small. So this is mechanical filtration or sieving. But in case the particle size is huge, then it won't be able to pass through the membrane, it will be retained here. So this is simple mechanical filtration or sieving. But when it comes to ultrafiltration, other than mechanical filtration, there is also steric hindrance. So steric hindrance is especially for large molecules or particles. So because they are very large, they won't be able to pass through the pores. So that will be there. And for nanofiltration, there is also charged base rejection. So like I had explained previously, so if the charge is similar, then there will be repulsion, and if the charge is opposite, then it will get attracted and it will get retained on the membrane. So that is there. And for RO, there is size exclusion along with solvent drag. So, other than the mechanical filtration, there is also a drag force by the liquid which is flowing. So, this will tend to drag the pollutant through the membrane or through the pore. And there are different types of flow also. So the first one we can classify as cross flow filtration. So here the feed water is tangential, meaning if the membrane is like this, then the water will flow in this direction. So as it flows through, it will pass through the membrane and the clean water will be collected here. So this is the cross flow, or the flow is tangential. And the second and the next one is direct feed. So here there is no recirculation. Usually what happens is whatever water is retained on the membrane, so that will be recirculated. So that kind of flow is the recirculated feed. So here the water, whatever reject is there, that will be recirculated. So recirculation will reduce the cleaning time, and it will also reduce the what to say the it will also help in increasing the life of the membrane, and it will prevent fouling. That's because the cleaning happens two times, and the water, the pollutant load is not very heavy. So that is why we need, when it comes to direct feeding, there is no recirculation. So for the recirculated feed, we store the retentate separately and then we recirculate. So compared to recirculated feed, for direct feed, the requirement of cleaning is slightly higher. And then there is this term, while designing membranes, it is very important to incorporate and find out what is the transmembrane pressure. So transmembrane pressure means the pressure gradient across the membrane. So we have a membrane and we have two sides of the membrane. This is the first side, which is the feeding side, and then the second one is the output side. So this side is the inlet and this side is the outlet. And the pressure difference across these two sides, so let's call them P1 and P2. So the difference between the pressure between P1 and P2 is your transmembrane pressure. So here the P1, it is actually made of two components, because on the inlet side we are dealing with two kinds of water. One is the feed water or inlet water, and the second one is your retentate. So both are going to be on the inlet side only. So both of them will also exert pressure on the membrane. So the feed water pressure is PF and the retentate pressure is PC. So retentate is also called concentrate, so that's why it's called PC. So here on the inlet side, we have these two liquids, so they will exert pressure on the membrane. And that's why for the inlet side, we have to take the average of these two pressures. So for the inlet pressure, this is PF plus PC divided by 2. And on the outlet, we only have the permeate pressure, which is PT. So your transmembrane pressure is the inlet pressure minus the outlet pressure. So this is equal to PF plus PC by 2 minus PT. So I'm just substituting whatever I've written here. So the inlet pressure is this, and the outlet pressure is this. I'm just writing everything here. So this is your transmembrane pressure. Then there is another term called recovery rate. So the recovery rate is actually a ratio, the ratio of permeate flow to the total feed flow. So suppose we have 1 liter of water flowing through the membrane. So the inlet feed flow is 1 liter. And the permeate flow, which is maybe from 1 liter, we might get 0.6 liters or 600 ml as the permeate. So then the ratio or the recovery rate becomes 600 by 1000. So That is just one example. And then we have something called the rejection rate. So rejection rate is the percentage of the constituent removed. And for example, if you have TDS and passing the water containing TDS, we get 90% TDS removal, then the 90% is your rejection rate. Okay. So, any questions so far on AOPs or membrane processes, disinfection? Is my voice audible?
Yes, ma'am.
So now let's look at the challenges in the membrane process. So the first one is membrane fouling. So we've already seen what this means. The second one is high energy consumption. The reason why there is high energy consumption is because we have to apply high pressure. So maintaining that high pressure requires more power. So that is why there is more energy consumption. And also, this process is highly unsustainable. So can someone tell me why this process is unsustainable? Why is this process unsustainable? Why are membrane processes usually unsustainable? How many of you have RO plant at home? Does anyone have an RO plant at home? RO filtration plant at home? Yeah. So, yeah. So after every 3 to 6 months, what do we do? We have to change the membrane, right? Yeah, not cleaning actually. So it's like the membrane gets fouled, and that's why it needs to be replaced with a new membrane. So, what do you do with the old membrane? Exactly. So, when you discard it, that becomes a solid waste. And discarded membranes are useless. They just contribute to more plastic and more waste to the environment. And because they are already having pollutants, they may also be toxic for the environment. It is not recyclable. No, our membranes are not recyclable. Maybe like they are developing processes or membranes which are recyclable, but as of now, we don't have recyclable RO membranes. So once you discard the membrane, it's like a solid waste only, so it contributes to more pollution. So that is why this process is highly unsustainable. So it is not good for the environment in the long run. So unlike other processes like AOPs or advanced oxidation process will completely remove the pollutant, but in membrane processes, the membrane itself gets loaded with the pollutants, and once it is fouled, it has to be replaced, and that creates unsustainability. Now we look at the different types of membrane damage. First one is corrosion. Cleaning method, not understanding. Yeah, it falls under plastic waste. Basically, it falls under the category of solid waste. So, and that cannot be recycled also. So, it's a non-recyclable waste. So, because most membranes, the core of the membrane is usually made of plastic, so that's why it can be a plastic waste also. Okay, so first type of membrane damage is corrosion. So this usually happens. Can you hear me? Okay. Okay, so there was a small disconnection. So we are back, and yeah, types of membrane damage. First one is membrane corrosion. So this can happen because of some wear and tear, or maybe the feed is highly acidic. So in those cases, the membrane could get corroded, and there could be some small wear and tear. So that is one type of membrane damage. The second one is pore narrowing. So here, what happens is like maybe if we have a membrane and this is the pore. So some of the I mean, if the pores are like continuous like this, and if the pollutant is retained by the pore, so it just sits here. So it is slightly blocking both the pores here. So similarly, if we have another pore here and the pollutant blocks this portion also. So here the size of the pore is now narrowed. So at the top and at the bottom we have two different particles so that are retained, and this reduces the size of the pore, effective size of the pore. And eventually, what happens is if we have a feed which contains some salts, then what happens is over this pollutant, there will be some salt layer also. So the salt layer may also get deposited over time, and that will reduce the size of the pore. Now, salt can also directly sit on the pores, and it can reduce its effective area. So that these two can happen. So pore narrowing is that. And then there is pore plugging. So pore plugging means the pore is completely plugged up. So like if a pollutant is big enough to get retained, then it will just come and it will sit on the pore and it will completely block it. So that is pore plugging. and then formation of a cake or a gel layer. So this is very common, usually seen in RO membranes. So with time, if there are any colloidal solids present, then they will form a gel-like layer on the pores. So the next time you replace the membrane, just observe the membrane. I'm sure you will find this gel layer on it. So uh, all these are the types of pore damage. So this gel layer will kind of trap the pollutant and it will not allow the pollutant to flow through, but over time it will block the pore itself. And how do we prevent all this? We have to pre-treat the feed water, and this is done by filtration and disinfection. Because if we don't disinfect the feed water, then there could be microbial growth also. So microbial growth can happen on the membrane, so that can lead to pore narrowing. So to avoid all this, it's better to always filter and disinfect the feed water. And how do we maintain these membranes? For maintenance, we can do backwashing, back flushing.
Voice is not coming, madam.
Is it still not coming? Oh, Oh,
I'm
I'm extremely
extremely
sorry.
sorry.
I
I
thought
thought
I
I
was
was
not
not
muted.
muted.
Okay.
Okay.
So,
So
back
back
flushing
flushing
and
and
then
then
chemical
chemical
cleaning.
cleaning.
So,
So
chemical
chemical
cleaning
cleaning
is
is
like
like
if
if
the
the
backwashing
backwashing
process
process
is
is
not
not
very
very
effective
effective
at
at
removing
removing
pollutants,
pollutants,
we
we
go
go
for
for
chemical
chemical
cleaning
cleaning
where
where
we
we
use
use
some
some
chemicals
chemicals
to
to
remove
remove
the
the
uh,
uh,
particle
particle
that
that
was
was
blocking
blocking
the
the
pore.
pore.
Okay,
Okay,
and
and
then
then
coming
coming
to
to
some
some
other
other
metrics
metrics
like
like
silk
silk
density
density
index
index or SDI. So SDI is ratio of 1 minus Ti by Tf divided by the total time T. So here Ti means the time to collect first 500 ml, and Tf means the time to collect the final 500 ml. So what this means is when you have a road membrane and you are using it for the first, I mean, when you turn it on and the time that it takes to collect the first 500 ml of the treated water is your Ti. So for example, if we have maybe 3 liters of water and we are passing it through the membrane and it takes about 15 minutes to collect the first 500 ml and we let it run for some more time and then when it reaches the final 500 ml, so that also we have to measure. So what we can do is we can take the 3-liter feed water, allow it to pass through the membrane and turn on the timer. So, and then every 5 minutes we make a note of how much water has passed through. So then we will be able to see how long it takes to reach the first 500 ml and how long it takes to collect the last 500 ml. And then we can divide the Ti by Tf and 1 minus Ti by Tf into 100 divided by the total time T will give you the silt density index. So total time means like if it takes about 45 minutes to completely filter out the 3 liters of water, then the 45 minutes is your total time. And Ti is 15 minutes, and maybe Tf is like another 15 minutes or 20 minutes. Okay, and then we have another parameter called the modified fouling index. So, unlike the silt density index, where we only record the time that it takes for the first 500 ml and the last 500 ml. So, in the modified fouling index, we record the volume every 30 seconds. So, we start the flow and then we start the timer also. So, every 30 seconds, we see how much volume has collected. And this is done for 15 minutes. And then we use this equation 1 by Q equals A plus MFI into V. Now this equation is of the form y equals to C plus Mx. So this is an equation of a straight line. So if you have x and y axis, then it will be like this. So here your m is the slope, and this c is the intercept. So if you make a plot between y, which is 1 by q, so q here is the flow rate, and 1 by q is the inverse flow rate, which is 1 by the flow rate. So if you find out 1 by q and you also know what is the volume, so volume is what you are recording every 30 seconds. So, and we also have to measure the corresponding flow rate for that volume. So if you have these two data, then you can just plot it. This is y, and the volume on the x-axis, 1 by q on the y-axis. So if you can just make a plot like this, then you will get a straight line like this, and from the straight line you can get the slope and the intercept. So the slope will be your modified fouling index or MFI, and the intercept is the constant A here. So then all you have to do is, you don't have to do much. Already your MFI is there. MFI is the slope and A is your intercept. So that's it. You just have to find the slope. Okay, now we come to membrane bioreactors. Or MBR. So MBRs combine both biological treatment along with membrane processes. So this results in high effluent quality with low suspended solids. So this is important because when you have conventional aerobic biological treatment, so there we need a separate, first we will have one tank for aeration with mixing, where the microbes will come into contact with the organics and they will degrade them. So then whatever effluent is coming out of this, sludge will be taken separately, will be collected separately, but whatever effluent is coming out of this, the supernatant, that will be passed through the settling tank. So here the the liquid will be allowed to settle. So here more sludge will be collected, and the clear liquid will be passed through the next phase. So instead of having a separate tank for settling, we can combine these two processes in one using a membrane bioreactor. Why? Because in a membrane bioreactor, we are having a membrane. I'm just drawing roughly. So imagine this is the membrane and you are allowing the water to pass through it, and there are also microbes on the membrane which will degrade the water, degrade the organics in the water as it passes through the membrane. So this has advantages because you don't need a separate settling tank. Whatever sludge is there, it will be retained on one side. Imagine this is your feed water side. Then the sludge also will be retained on this side itself, and clean water will be coming out. So you don't have to retain it, build a separate tank for it, and allow it to retain and all that. So time is saved, and money is also saved. And then we have membrane aeration bioreactors. Or MABR. So this is also just like a membrane reactor, but one difference is that here we put the membrane, and along with that we also provide some aeration. So we provide some oxygen supply to the membrane, and there is also, because of oxygen supply, it can also the microbes can do nitrification and denitrification. So I hope you all know what nitrification and denitrification means. So nitrification is just conversion of ammonia to nitrate, or ammonium containing ammonia or ammonium to nitrate. And denitrification is converting the nitrate to nitrogen gas. So because we are supplying air, nitrifying bacteria can convert ammonia to nitrate, and after nitrate conversion, denitrifying bacteria can convert the nitrate to nitrogen gas. So because nitrifying bacteria require oxygen, so that is already being supplied. So the the membrane can have denitrification as well as nitrification processes along with conventional aerobic degradation of the organics also. Okay, one advantage of membrane bioreactor is that it can remove COD even at low BOD to COD ratio. So like we've seen how only if the BOD COD ratio is higher, only then we can go for biological treatment. But if we are going for membrane bioreactors, we don't need that criteria. Even at a low BOD to COD ratio, we can go for this kind of treatment. And then we have anaerobic hybrid membrane reactors. So this is like an upflow anaerobic sludge blanket. So
An upflow anaerobic sludge blanket is usually used for treating anaerobic sludge, and this is where the feed water is passed from the bottom, and there is a sludge blanket which, sorry, I'm not sure how this line came here. So here a blanket gets formed. So as it flows, as the water or the wastewater flows through the blanket, this blanket will have a mix of organics plus dead cells and also live organisms. So as the water passes through this blanket, it will be treated by the bacteria, and then the clean water will come at the top. So we can, in a hybrid system, we have both a sludge blanket, which is this, and along with this, we also have suspended bacteria. So the suspended bacteria can degrade the pollutant, as well as the bacteria in the sludge blanket can also degrade. So it happens in a hybrid way. Okay, another major disadvantage of waste membrane treatment process is that we need to dispose the rejectate also. So rejectate is usually discharged into oceans because it is highly concentrated. So it can only be disposed. So one way is to discharge it or let it out in the ocean, or we can also use it for land application. Land application means simply disposing it on the land. So that's, I mean, there is no. And then we can also go for deep well injection. So this is where we construct a deep well and under the ground, and then we will inject the RO water deep inside the well. So after injection, it will go and it will penetrate into the soil. And the next one is evaporation. So you can also evaporate the reject. So evaporating the reject means we will get some solid residue, which is the salt and the pollutant itself. And then another one type of evaporation is, one can be natural evaporation. So the other is controlled thermal evaporation. So, like someone asked if we have some recyclable membranes. So, people are working on it. So, we are developing smart membranes. So, smart membranes are anti fouling and self healing. They have especially materials which can prevent falling from happening and therefore clean themselves. And then we can also integrate them with nanomaterials. So this is a very popular technique, nanomaterials integration. So we can coat the membranes with nanomaterials. So these will ensure that the uh, pollutant gets retained without fouling the membrane. So we can
have some like there are different nanomaterials available, so all of those can be coated on the membrane surface to prevent fouling from happening and also increase the rate of rejection or the pollutant removal efficiency. Okay, so if you all are interested, we'll be solving a problem now. So shall we go ahead or shall we end the session? Okay, I'm just going ahead with the problem. Okay, so it's a very simple one. So this is based on the SDI test or the silt density index. So the question is during a SDI 15 test, the initial 500 ml collection time equals 30 seconds, and the final 500 ml collection time is 90 seconds. So calculate the silt density index or SDI. So if you could recall, silt density index was 1 minus Ti by Tf into 100 by T. So can you all tell me what is Ti, Tf, T, etc. All of them. What is Ti here? So I've given you two times, right? Initial 500 ml is 30 seconds and the final 500 ml is 90 seconds. So what should be Ti and what should be Tf here? You can even type the answers if you're not interested in speaking. What is Ti and what is Tf here? Yeah. So Ti is 30 seconds and Tf is 90 seconds. And what is the total time T? That's a trick question. No. See, the total time is not the sum of the initial 500 and the final 500. For example, if you have 3 or 4 liters of water, if you combine both, then it will only come up to 1 liter, right? What about the rest? So here the answer is in the question itself. So here I mentioned it is SDI 15. So this 15 here denotes 15 minutes. It means the test or the collection was done for a total of 15 minutes, of which the first 500 ml was collected in 30 seconds and the final 500 ml was collected in 90 seconds. But the total time that it took for all of the feed water to pass through the membrane is 15 minutes. So the total run time is 15 here. So SDI 15 means the test was run for 15 minutes. So T here is 15 minutes and Ti is 30 seconds and Tf is 90 seconds. So can you substitute and tell me the answer? what should be the answer? You just have to substitute and tell me the answer. Yeah, so it is 4.45. So generally, if the SDI is more than 3, it means we need to have pre-treatment. So why the pre-treatment is required? Because here we are taking the ratio of initial 500 to final 500. So we will get a higher value of SDI if the initial time or TI is very much lower compared to the final time. So if that happens, it means the pore is getting blocked as the water passes through the membrane. So that is why we need some kind of pre-treatment to remove any solids or some blockage causing substances from the feed. So with this, we've come to the end of today's lecture. So if you have any questions, let me know. Do you have any doubts or questions from today's class or the previous classes? Yeah, you have a question? You want me to explain how to calculate ppm? Okay, that's very simple. So for water, because we have the specific gravity of water is 1. So this is true only for water, not for other solvents or for air or for any other medium. So only for water, uh, ppm is equal to milligram per liter. So whatever you have in milligram per liter, let's say 1000 milligram per liter equals 1000 ppm. This is only true for water only, not for any other medium. So only for water this holds true. Like whatever concentration is expressed in ppm is the same as milligrams per liter. Okay. So any other questions or shall we end the session? I'm not understanding how to calculate. What is POI dose? Your question is not clear. Poly, not understanding, like as in polymer. Can you be a little specific? Like, I'm not getting the context of this question. So, poly can mean a lot of things. So, okay, that's okay, but you can still type the question. Okay, so if there are no further questions, we will end the session today. Thank you all for joining. Let's see you in the next class.